All right, welcome everybody to this webinar, and thanks Hannah for the introduction. So today we're going to talk about this topic of high fidelity simulations of mechanical systems, and especially we're going to talk about how are we able to accomplish these high fidelity simulations, and how do we make them available to the non-expert user. And this is really a special topic, and something that I think is, as far as the case study we have, this sort of work is, I think, rarely shared, because people who do the work to come up with a special simulation system tend to keep it private, as there tends to be proprietary information, and it's also, becomes a very strategic tool. But in this case, we have some work that we did under a government research grant, and so we have this very rare opportunity to be able to share some of the details of that with you. So by way of introduction, let's talk about what the problem is we're trying to address. And as you know, many people believe that it can be very important to have custom user interfaces to enable non-experts to create, run, and be able to review and comprehend the results of complex CAE applications. And I think these days, some organizations have dedicated CAE analysts whose full-time job is to do CAE runs. But many other organizations rely a lot upon project engineers and product engineers to, do the simulations as part of, the overall design process. And so in those cases, the engineers are definitely experts on their products, but aren't really full-time focused on simulation. So therefore, to have custom tools that really address the particular process that needs to be done can be very important. Likewise, this ability to, put into the process some process automation so that, for the typical simulations that are run in the organization, that the tedious part of it can be automated out to be, very fast, and that, provides a more efficient environment and a better user experience. So that's the need. So then the question is, what's the cost to develop such tools? And I know, like a long time ago, IBM studied, what was the cost for in-house software as compared to off-the-shelf software. And this was really quite a few years ago. And at that time, the ratio was a factor of 10. So in other words, it cost 10 times as much to develop the in-house CAE or tools or any kind of software, actually, as compared to off-the-shelf software. So today we're going to look at this case study, and it's going to look at the use of the RecurDyn multibody dynamic software as a platform, basically a multi-physics platform for an updated version of the NATO Reference Mobility Model, or NRMM, which is a tool used by many organizations, mainly military organizations, as a way to have a common reference to compare the mobility of the different combat vehicles for all the NATO countries. And this NATO Reference Mobility Model has really been around for quite a while. It developed in 1974, upgraded in 92, and again was enhanced in 99. The current capability is considered to be basically, limited, and part of that is because even these enhanced versions were developed, over 20 years ago, when computers were much slower and limited. So therefore, the NRMM is not using all the latest approaches that could be applied to vehicle dynamics. And So then the question is, you know, what's the next logical step? Is it possible to go through another enhancement, or should a new tool be developed? And what should the proper approach be? So because of that, there was a small business innovative research grant that was awarded to us to fund some basic evaluations of what could be done to develop a custom application. And the idea is it would be built on the RecurDyn platform. And the question is, what kind of enhanced capabilities could be demonstrated? So this diagram here shows the basic architecture that we developed. And so you can see on the left with the RecurDyn block, there's various aspects to the software. And you know, that we have to worry about issues of, you know, being able to do the proper calculations, the proper simulation, and be able to obtain high fidelity results. That's one part of it, is just all the computational aspects. The other part of it is the graphical user interface aspect. You know, how do we have a logical process that the user can follow and not be bogged down with a bunch of manual steps. So as far as interfaces are concerned, you know, one aspect of a tool like RecurDyn is that there are many interfaces that are already in place because of the fact that it's, you know, built to be a multi-physics tool. And so as we look at some of the interfaces that exist, then we can look and evaluate how they compare as far as needed capabilities, but also how do they compare with custom modules, you know, that are needed by the NRMM. So, you know, one is flexible bodies, and which can be represented as, you know, linear mode shapes or as a nonlinear flexible body. So that can be used to model different aspects of the vehicle system. And actually, you know, NRMM was not doing that before, so you know, that's just new enhanced capability to be able to do that, and it can be done within the standard RecurDyn tool set. And then there's a standard tire interface to third-party tires, and so therefore that can be used, you know, as it exists to interface to any kind of specialty tires that are developed for the NRMM or to the current tires. And then there's a standard particle interface for discrete element modeling, and that also already includes an interface to the EDEM, you know, DEM software, which can be used for Terra mechanics to look at contact between tires or track with the ground, with soft soils. And then we have a controls hydraulic interface with, you know, direct support for Simulink. For controls, Amazon for hydraulics, general, you know, APIs to do that kind of interfacing and so forth. And, you know, we'll see a little bit later on how that can be used to look at things like driver models and also even autonomous vehicles. The general model database, you know, consists of being able to import as well as generate solid geometry. There's a variety of toolkits for all sorts of machinery, including track assemblies. And track assemblies include soil subroutines, so that can interact with data from the EDEM soil model. We'll look at that a little bit later. And then a little bit further down here, this whole area of design optimization, you know, design of experiments and the nonlinear system level optimization. And in particular for NRMM, there's a high interest in enhancing capabilities for what's referred to as uncertainty quantification, or UQ. And so that really consists of, you know, having careful planning for the DOE to run many runs and then to derive sensitivities and so forth, and use that as a basis for understanding the system, but also for optimizing the system. And then, you know, RecurDyn can do all this interfacing and then have, you know, one solver environment to solve this multi-physics type of model. So I'm sorry about all the text on this slide, but we're going to focus on these highlighted phrases. But this is going to introduce what we're going to look at. And so what are the benefits of this approach of using a tool like RecurDyn as a software platform as compared to writing the software, from scratch, totally new. And so, here's, and then, the other question is what kind of capabilities does RecurDyn have to enable, certain key functions that need to happen in order to not only develop, but to sustain and support this kind of application. So the first one is, the fact that the enhancement and maintenance of the RecurDyn software itself is basically co-funded by a broad community of users, and from many different industries. And that's quite important because when you look at a tool, like NRMM that's going to be used by a certain number of agencies, so maybe we're talking about a dozen different agencies who are going to use the software heavily, and maybe a similar number of like governmental contractors. And so if everything is done from scratch, then the small group has to fund, everything, and that becomes difficult to sustain that over time. And in fact, that's one of the reasons why the NRMM software kind of fell behind, just because, how can there be enough money to keep up with everything that's happening in the mechanical computer-aided engineering area of software. So by having it be, the platform be a general purpose tool, that it's co-funded by many industries, and so now we're talking about many hundreds of companies who are all contributing to the enhancement of the platform. Second area is that, since RecurDyn is intended to be a multi-physics type of tool, then it includes a lot of interfaces, because we've always had the approach of interfacing to other software wherever possible, so that we could really offer very advanced capability and leverage what other companies had done. And that's why, so these interfaces to the controls and to EDM and other things, Particle Works and other software is all part of the general strategy. So the fact that those interfaces are already present means they do not have to be developed as part of NRMM. Third one is that there's open architecture with documented user interfaces, application programming interfaces, and subroutine interfaces, all of which are available for independent developers, and whether that's individual customers or a research team, or us EngineSoft, doing work on capabilities through those interfaces. The point is they're available to everyone, and then they can freely go and make enhancements to the software, and then those enhancements then can be applied to new releases of RecurDyn as it comes out. Fourth, these add-on modules, whether they're subroutines or functions developed with the APIs, people can choose to make those open source, open architecture, and release them to a broad user community and let people modify things. That all can be done separately, and then basically integrated to then form up the upgraded RecurDyn package that then can be used for the actual simulation. Fifth, so the amount of work that's needed is reduced when using an existing platform. So any kind of multi-physics capability doesn't have to be redone, as well as the other off-the-shelf, COTS is commercial off-the-shelf. So other commercial off-the-shelf software that RecurDyn interfaces to, all those capabilities don't have to be recreated. So then the focus can be on the custom capabilities that are particular to the NRMM. and you know, things like you know, special data storage tasks and so forth that are needed for these kind of simulations. And then number 6, as far as the RecurDyn platform, since we work with so many different industries, all sorts of products of different scales, different levels of complexity, different approaches, it's basically a matter of reliability and comfort to know that, you know, many other models have already been handled. So it's, you know, as compared to doing everything new, where everything would have to be all tested out, you know, just as far as the broadness of what can be handled. In the case of RecurDyn, that's already done by the overall broad user group. And then finally, the verification and validation work of the solver results, all, you know, thousands, many, probably tens of thousands of tests are done with each release of RecurDyn, making sure that all the numerical calculations are being done correctly. And many of those tests are then developed or have been developed in comparison to closed form equations. So then we compare our results to those approaches just to make sure that everything is precise and accurate. Okay, so with that introduction, let's look at what the challenge is on NRMM. And so, you know, this tool is to look at off-road capabilities of vehicles, whether they're wheeled vehicles or tracked vehicles, you know, with the idea is if there's some sort of conflict and you have multiple NATO countries working together, you want to know what the mobility capabilities are of the different vehicles, because, for example, if a vehicle is not able to traverse the ground, it may end up blocking the road or the path, you know, so that the other vehicles can't come through. So nobody wants that kind of a problem. So in this case, you know, we're looking at interfacing, you know, the first goal here is to be able to look at interacting with geographical information systems or GIS systems. And that's something that, you know, most RecurDyn users are not too worried about, but in this case, it's a very important capability. And so this particular plot of ground is located in Michigan, Upper Michigan, and is in a remote area. And this is a, you know, basically a test course for a variety of off-road vehicles. And so, in the case of, you know, how is information about a terrain communicated, you know, and really how does the terrain even get described? So it turns out there's techniques, variety of techniques, different sensors, including radar sensors, can be used to evaluate what is the shape of the terrain. There's also information about the terrain characteristics, and we'll get into that more a little bit later. But in this case, we have this piece of ground 1 mile by a half mile rectangle here. And so we have information. So the question is, how do we bring it into RecurDyn? So the approach here is to use Processnet. And the file format that we're working with is a file format called GeoTIFF. And so these GeoTIFF files contain the elevation data. And so the point of the Processnet application is to read in the file and then create a three-dimensional terrain surface, or, you know, as referred to in the track assembly modules, you know, a road. And likewise with the tire modeling, we have the concept of, you know, the same terrain or road that the tire or the track interacts with. And so the application was developed. Since Processnet is running in Microsoft Visual Studio, then it can access, you know, many languages, many tools, and different development resources that work with Microsoft Visual Studio then are ready to use, you know, to enhance RecurDyn. And so with our research, And by the way, I should give a shout out. Nelson Wu did much of this work for this project, and especially did all of the Processnet work, and he's super skilled at that. And anyway, so he went and looked and found an open source library called Geospatial Data Abstraction Library. And then he found that there were different language bindings that could be accessed. And Visual Studio supports C#, and there was a C# binding, so that helped make it more straightforward to be able to use that library. And so then and the Processnet application can use that library to import the GeoTIFF file and then generate bitmaps. And the bitmaps can be expressed as in a grayscale, where black is the minimum elevation or the lowest elevation, white is the highest elevation. And then likewise, you can also generate this color scale bitmap where blue is the minimum and then red would be the maximum. So then this bitmap and this information then is used to create a RecurDyn road data file. And the road data file contains points and then definitions for polygons. And so then after the file is created, then the Processnet application imports that file into RecurDyn. So, so the first goal then was to read in the file. Second goal is to generate the 3D ground definition, and this shows, you know, the output. And if you look at this image on the right, you can see, you know, basically different changes in elevation that map up or correspond with the color bitmap images we saw earlier. But this is actually polygon-based terrain, and the vehicle, in this case we have just a generic tracked vehicle, can actually operate on this very complex terrain. So next slide, we're going to look at what that is like. So here's our tracked vehicle, and here's this very large terrain. And actually this tracked vehicle is more like an autonomous tracked vehicle, not like a full-sized military vehicle. It's a smaller tracked vehicle for reconnaissance and so forth. But anyway, you can see all the details of the terrain. And so basically the user is able to now just import this GeoTIFF file and have this terrain generated. So now the user doesn't have to get into all the details of the GeoTIFF file. By using the Processnet application, he can use this data, get it very quickly. And this is, you know, really advanced capability to be able to have this level of detail. And this is just showing a few lines of code, but, you know, just to see all these different function calls. So it's just C#, but it can be any .NET language can be used with Microsoft Visual Studio. So it's just regular coding is used, but the user is just working with the library file to be able to run the application. Okay, so then goal 3 was to look at mapping of soil characteristics. So it's not exactly prevalent today, but the hope is that as time goes on, that not only will there be information from the GIS system about the terrain shape, but also information about different aspects of the terrain and the soil. So things like how much moisture is in the soil, or what kind of vegetation might be on the terrain, and various attributes like that, or, you know, could be obstacles, like if there were to be, like, you know, sizable boulders or something like that that would you know, be something that you would not want to drive over. All that information is desired to have as part of the file. So we wanted to look at what it would take to use that kind of information. So in this case, we took the GeoTIFF file, and then we, you know, added information here, and we just wanted to do a straightforward example so that we could track through what was happening and then make sure it was working right. So in this case, we have the soil characteristic. It varies from 0 to 50. And as you can see, it starts with a low value, goes to a high value, and then comes back to the low value. And so that's shown with the bitmaps. It's shown in the plot in the lower left corner. And then in the lower right corner, we see a plot that we have that relates some of the soil characteristics for a Becker soil model, BEKKER. So Becker did a lot of research decades ago on tracked vehicle mobility. And so he had a way to characterize soil with an equation that had 7 parameters. And so these are 2 of the parameters that have to do with the stiffness of the soil and then also a cohesion value. So with both of these values, as the characteristic number goes from 0 to 50, then these numbers are decreasing. So the soil is getting softer and less cohesive. So then what would we expect to happen? So in this case, we have the vehicle traversing, and now it's starting to go through. You can see that with the less cohesive soil and less stiff soil, then this you know, it's a heavy vehicle, so it sinks down into the soil because of the lack of stiffness and cohesion. So you can see here's the biggest sinkage, and then as the soil gets stiffer on the other side, then it kind of climbs back out. Okay, so the idea would be, you know, what's desired is to be able to have this terrain with the soil characteristics. And what we have working here is we have a communication between the terrain and properties of the track interaction with the soil, so that we're getting this interactive changing of characteristics. And so this is, I think, very advanced capability. Usually it's not so common to be changing, you know, basic model characteristics during a simulation, but with this approach here, we're enabling that, and so that the soil characteristics being seen by the track, you know, is totally defined with the terrain. So that provides a lot of capability. And then, as I mentioned, there's things, other attributes besides the soil attributes would be things like trees and rocks and so forth. So, you know, as we've talked about before, you know, you have the elevation data creates the surface, but then there can be other data, in this case, to represent, you know, the trees, some information there. So the idea is that in the Processnet, there was algorithm put in there to be able to look at, you know, this variable related to presence of vegetation and tall vegetation. And so then we had a certain threshold value, and then, you know, we decided when trees were above a certain threshold, I mean, small trees, you know, can be pushed aside by the vehicle, but large trees cannot. So if the trees were larger than a certain value, then we set up obstacles. And then where there were obstacles, we actually updated the terrain to create some terrain features, you know, to make those obstacles apparent. Okay. And so then we then, well, for all the different things we've been looking at, you know, we need a user interface to support that. So in this case, we're looking at the user interface that was developed, again, using Processnet. And this is where the bitmap images are being produced, but it's also producing information about the terrain. So this is showing the min and max elevation in meters. And it has soil parameters available on the right, and this is, you know, a library of soil parameters from RecurDyn, but then we also add the ability to override those soil parameters with information from the terrain. And if you look up at the tabs in the upper left, you can see that 2 parameters were found in this terrain file. One was the stiffness, one was cohesion, and so basically, the way this is set up is that Processnet will create as many tabs as needed according to how many different parameters are included, in the GeoTIFF file. And so, the user simply comes in, selects the file with the GeoTIFF file, and then once that's selected, then the information is then brought in, and then the user can review things, make some changes, and then click OK. And if we want to look at what's on the other tabs, so this one is showing the elevation, and then here we're seeing some mapping here for the K sub C, or the stiffness. And you can see where the roads, there's certain dirt roads and so forth, and they're stiffer. And then we have also a mapping of the cohesion. So let me back up there. Okay, just want to make sure I didn't miss anything there. Okay, and so then, the user can go between the different tabs to gain an understanding of the terrain. And as I mentioned, the soil parameters from the library are available, to then, contrast that with what's coming in with the file. Okay, now we're going to look at autonomous vehicles. So we see the blue is showing a target path for the vehicle, and then the red is showing the actual path that it's taking. And the idea is that, well, actually the blue path is the target path because it was done with some specialty software called pre-scan that's used, for the obstacle avoidance. And then what we did is we then also put together a capability to do it directly in RecurDyn. And so these white lines coming out from the center of the vehicle represent sensors, and then that sensor data is used to guide the vehicle. And so on the top view, we have the view, looking from the top, and then on the bottom we have this ISO view, and you can kind of get a feel for the fact that this terrain is not level. And we can also see the vehicle is doing a little bit of sliding on some of these corners. So, that's the value of this kind of high fidelity simulation, is that you can see what the accurate behavior is, without it being idealistic and everything, working perfectly, like, in other words, not sliding at all. But in real life, they're sliding. There's also delays because of the controls and so forth. And all that can be considered here. So this is showing one of the control systems that was developed. This is in MATLAB, and there was interaction with the pre-scan software through MATLAB. And these different sets of similar looking blocks of data are corresponding to the different sensors. There's 8 total sensors, and so we can see the block for each sensor. And if we look at the next slide here, we can see information here. Again, similar to what we were looking at before, the top view, but you can see the sensors now more clearly. And you can see with the interaction with the obstacles, things are a little bit different. When there's not so much going on with the obstacles, then the vehicle's tracing, very well. So there was 3 different runs that were done. One was with RecurDyn and the pre-scan software, again, using MATLAB as the intermediate software. And that's just, again, part of the interfaces of RecurDyn, being able to use FMI, being able to use MATLAB, being able to use a library, with a programming interface and so forth. All these different things, can allow interaction with, other tools. And, pre-scan is a very specialty tool that has a lot of intelligence for avoiding obstacles. Anyway, so that was one simulation. Second simulation was done with CoLink being the controls package, RecurDyn CoLink, as opposed to MATLAB, and then also the sensors and all that logic that was happening in pre-scan was also added to CoLink, so that everything was modeled within RecurDyn and RecurDyn CoLink. And then the third one was just the vehicle, having a very basic controller to follow a pre-described path. Not looking at any obstacles, no sensor logic. And so the reason we're talking about this comparison is that we want to compare the execution time. And we can see that with no logic at all, as we would expect, it's the fastest time. But if we look, the fastest time being 18 minutes, 45 seconds versus the slowest time of 20 minutes, 18 seconds, they're pretty close in time. And what this tells us is that the logic for controlling the vehicle is a fairly small amount of the burden on the CPU, on the computer, as compared to the needs to simulate the tracked vehicle and the interaction with the soil and so forth, which is good. So this means we have some options here with the controls, and it won't drastically slow down the simulation. Okay, another area for NRMM is physics-based vehicle dynamics. And so here we're looking at an example of a wheeled vehicle. This is called the FEV vehicle, or FED, sorry. And it's a fuel efficiency demonstrator. So it's doing some special things with hybrid technology and different things like that. And in this case, we're looking at a particular maneuver, which is just, acceleration down the track at full throttle. And so on these different plots, we can see velocity in mile per hour. So it eventually gets up to about 85 miles an hour. And then the middle plot is showing us the gear changes. And this is I think 5-speed. And then on the bottom, we're looking at the engine torque and as a function of time. So that's going to be the speed of the engine is going to be varying with the gear that it's in. And you can see that when it shifts to the next gear, the torque jumps up because the RPMs are slower and so forth. So there's actually many different mobility events of interest, and this one is just one of them. And in this case, there's a user subroutine that's used to control the shifting of the transmission, and we'll cover more about that later. Over here on the right, we can see with the vehicle, we're using some force vectors to show torques and vertical forces, at the wheel centers. So this is showing some of the inputs that go into this wheeled vehicle. So we have a detailed model of the steering assembly, and then the suspension, and then different tables of information. So this is the air spring for the rear suspension, and that's expressed as basically a lookup table. So we have different Y values, different X values, and then values in the cells are the Z value from the table. So we can be varying two different aspects of the suspension behavior, and then be able to extract the proper damping force. And on the lower left, we have a plot with the engine torque as a function of speed. And so we can see, it's a typical torque curve, and so that's used, in the system. So, this is another type of interface that exists, is just the ability to pull in the splines or lookup tables of interest to be able to track them. This kind of activity can be done within Processnet, or it can be done manually by the user. It just depends on whether or not there's a tedious aspect of it or not. And then actually with the spline data, you can have it associated with the external file, so the things automatically update by just swapping in a new file, but the model itself doesn't have to be changed because it's going to update with the file name or with whatever the contents of the file are. And then this is looking at the bottom left here is the overall powertrain, topology, logic topology here. And so these are all the different interactions that are happening. And then you can see, this interaction of looking at the engine, RPM coming out of the PTO, and then applying the transmission gear ratio, and then you finally have an output shaft RPM. And then this lower right is a table that's showing, what is the gear that's going to be selected given speed and, like the torque requirements. And that will determine how things get shifted. And so all this information is actually for the shifting is done in a user subroutine. And you can see in this overall strategy, we have, according to the color of the arrows, we have certain things being, information being conveyed as parameters. Could be calculated items, and it could be user subroutine calculated values. So then, again, probably a dozen different mobility cases to look at. And here are two of them. One is a turning radius test. So just to say, okay, if the vehicle, if the steering is turned hard to the right or left, then, what is the actual turning radius? And, this has to do with, some things like tire slip and so forth. And you can see that the measured information versus the calculated information, is very, very close. Another mobility event is a NATO double lane change. So the vehicle enters the test track, does a lane change to the left, and then comes back to the original lane on the right, and does so without hitting any of these cones. And the question is, how fast can that be done? So this dialog box on the right basically shows, the inputs that can be provided. And, basically these selection boxes allow the user to pick the different tires and so forth. And what happens with that is that once those things are selected, and up here you can see, selecting the steering control joint and so forth. By selecting those bodies, then the Processnet application not only will construct this terrain according to the basic dimensions of the vehicle and so forth, but it will also, connect certain things to the vehicle so it can control the steering and so forth. And you can see that there's support for wheeled vehicle or a tracked vehicle. And so then we have a basic representation for a driver. And so the driver, there's two things being controlled. One's the steering and the other one is the throttle setting. And then looking at the results, this is showing at 40 miles an hour, the FED vehicle is just, almost touching the cone. Here, both on the left side, as well as on the right side here. So it's right at the boundary of hitting something. So here we're going to look at the actual simulation. So here we have a head-on view, we have an overhead view here, and then here we have a zoomed in or a zoomed out view, just a larger view looking at the vehicle and comparing two speeds. So the blue curve is showing the vehicle at 40 miles an hour, which it traverses the course, almost touching but not touching. And whereas at the next increment of 42 miles an hour, the vehicle cannot maintain control and actually exits the course right there. This image at the middle left is showing the vehicle in the middle of some of the steering, and you can see, again, forces at the wheel center and torques. you know, to provide some perspective. You know, of course, when the translational forces head towards zero, that means that the tire is ready to lift off. So in some vehicles, that can be a real issue. You can see here, it's getting a little bit of sliding, you know, and that's why I was getting so close to the cone. So to be able to do this kind of advanced simulation, to do it manually with a, you know, just a standard general purpose multibody dynamics tool would take a long time to manually set up the track, manually set up all the different aspects. But with the process automation of Processnet and the custom dialog boxes, now this is so much more approachable, and the user can go through these activities and not have to worry about the very intricate details of every single little coordinate system for connecting things up and things like that, but rather can focus on the basic engineering questions according to the, you know, the custom interface that's being presented. So with the lane change operation, we can also, you know, plot these different outputs, and we can have Processnet create these plots. So in this case, we have lateral and vertical tire forces, and this is at the, you know, sort of almost limited speed of the 40 miles an hour. And we can see what's happening with the different forces as a function of different locations on the course. Okay, another area of interest was physics-based Terra mechanics. And actually, this is a huge topic to be able to understand what's happening with soft soils. It's very complex. You know, the behavior of a soil varies with location. You know, what is the content of the soil? But even in the same location, the behavior of the soil can vary a lot, quite a bit with humidity, and maybe a bit with temperature and so forth. So what we did on this project is we used the Altair EDM software, and we created in RecurDyn a small model with just a few track links. And the idea of the first and the last track link is that they're there to establish boundary conditions, you know, the proper boundary conditions, but we're gathering data from the middle track link. And so here we're applying a normal force, and then we have this horizontal force representing the track tension. You can see it's quite balanced on the top image here. So basically we're applying a normal force, and the track surfaces are being pushed into the soil, being represented by all these particles. And by the way, there's 78,000 particles. Each one is made up of 3 spheres, so there's over 230,000 spheres. So the track gets pressed into the soil. That would just represent the vehicle sitting on the soil. And then what we're doing here is we're causing an imbalance on the force, the horizontal force. So we're increasing the force on the left, decreasing the force on the right to represent the torque, or sorry, the forces, you know, pulling the track to one side as the vehicle is trying to move in the other direction. And then finally here you can see that, you know, the force is reduced a lot. Anyway, so what happens is that, you know, the normal force, the weight is still on the track. And so the track segments, you know, dig into the soil as they get pulled across. So at some point, the resisting force is going to increase actually with velocity for a time. But then eventually when the track breaks loose, then the resisting force is decreased a lot, and the vehicle, or the track segments just slide to the left very quickly. So this isn't, the behavior is not like standard friction. It's different because, you know, the frictional forces, the resistive forces actually increase with the relative velocity for a time as things are digging in. But then once you get a high enough velocity, then it breaks free, and from that point of view, then starts acting more like regular friction. Another area is this uncertainty quantification, which means when we do a simulation, we can do it with nominal results, but then we want to be able to look at the variability in the design inputs. So this is an important capability for our client. And so they're looking at different tools for doing this uncertainty quantification. For this project, there was a tool called Ramdo that was being used. There are other tools available. So within RecurDyn, because of, we have the auto design product, but we also have a design study capability, and we have the capability to import and export information. So on the import button here in this design matrix, which is accessed with this button down here, you can create your own design matrix or have it created with one of the built-in techniques, but you can also import a CSV file, and that can come from any of the tools. So if the client has whatever tool that's going to come up with certain runs, that can be imported in, and then when the user says simulate, all the runs will be done, and then this result sheet button will become active, and then you can export a CSV file that shows all the different design parameters, how they've been changed, and then shows all the different results of interest and what those values were for every single run. And then that data can be used to then do sensitivity studies, optimization, and so forth. So this is just another interface example. So we've talked about many different things, but this is the nature of really having an effective multi-physics, high fidelity application for simulation, is that there are so many different aspects. And as we've seen with RecurDyn, there were so many different ways to interface with RecurDyn, with the subroutines, automation of the process with Processnet, formal interfaces to other tools, and so forth. And that's what it took to be able to do all this efficiently. And imagine if all that capability had to be developed, from nothing, it would really take a tremendous amount of time, be a tremendous cost, and that's why this doesn't happen that often. Is a completely, separate development project. So, again, what are the benefits? We talked about this in the beginning, but just to review what we've now seen is, with this RecurDyn being co-funded by this broad community, the broad community has already driven the creation of so many interfaces in different ways, which made it well prepared to do this custom application. And these interfaces are actually to other, multi-physics type capabilities, which then really allows for some high fidelity simulation. And we've seen how with this project, we were acting as an independent research team, but we were free to develop specialty modules to cover the needed capabilities. We were able to use, in our case, we did a C# language, but it can be various languages, and anybody can access them, and then you develop the capability and then compile up a library, and then that can be shared by all the different users. And the fact that so many things were done really allowed us to focus more on taking care of what was missing. And actually for us to understand the GeoTIFF files was not easy because we don't usually work with those, but because of all the other interfaces being present, we could spend the time, figure out what's happening with the GeoTIFF files, and then figure out how to use the data that we could extract from them. We could also think about, architectural framework, how we wanted to set things up, and also, how we wanted to check the accuracy of the data. And, since RecurDyn already handles, a full range of different types of models, we didn't run into any issues where RecurDyn couldn't handle whatever we placed within the model, and the verification validation was already done. So all the behaviors we saw were quite reasonable. So that's the presentation. And we have done, by the way, for other clients, we've done these types of projects. And again, a lot of times we can't really talk about them, but it's been some amazing capability. So I think, you know, for organizations that are looking for, you know, having an advanced tool that they can add some, you know, special capabilities and then enable their engineering staff to use it without having to be simulation specialists, you know, this seems to be a very good way to do that. So if anything comes to mind along those lines, feel free to contact us and we can discuss the possibilities. So thanks very much for your attention.